Hello, hello.
Hello.
Good
Hello,
morning,
hello.
Professor.
Good morning. Hello, good morning. Good morning. Thank you. Hello. Hello, Noella. Hello, Nikaya. Hello, Jean-Pierre. Hello, Noella. No, I'm not saying it right. Can you tell me again? No.
It's Noelia.
Oh, okay. Noelia. Okay. Thank you. All right. That's like, okay, cool. Good morning. Good morning, Jean-Pierre. Good morning, Jennifer. Good morning, Luna. I kind of like doing this. You know, there used to be a kids show like a long time ago called Romper Room with like 4-year-olds, and the teacher would always be like, hello, I see Pauline and I see Danny. Okay. Hello, Luna. Hello, Jean-Pierre. Hello, Jennifer. Noelia. And that's in, oh, and there's more people coming. It's like Yaverbaum. Every time I'm in a store or a restaurant or whatever, or like paying for something, and what's your name? Yaverbaum. And they're like, what? And of course, I'm always prepared to spell my name. Of course, I always have to spell my name. So, but it's always the same thing. It's like Yaverbaum. Okay, Y as in Yankee, A as in Apple, V, blah, blah. And I spell, and always when I get to the end, everybody's like, oh, oh, yeah, just like it sounds. Yeah, it's spelled just like it sounds. And I'm like, yeah, why are you angry about that? Right, I know, yes. So thank you, that is my name. But it is true that anybody in the world that I've ever met or that I know of who's named Yaverbaum, I know how they're related to me. Like I've never heard of Yaverbaum that I don't know how they're related to me. And I'm not saying that my grandparents were like cousins, but they were. And that explains a lot. Okay, what do we do? We're almost, hello, Antonio, hello. Um, sorry, Myrani, will you correct me later?
Marani?
Oh, Amarani?
Yeah.
Oh, that's just like it sounds. Oh, okay, yeah, Amarani. Okay, got it, thank you. And by the way, for those of you who are in a forensic science major, yeah, my name is Yaverbaum, and you know, it rhymes with cadaverbaum or cadaver town even. Isn't that convenient? Good morning. Yes, good morning. And how, okay, is it Shitali?
It's Sitlali.
Oh, okay. Oh, just Sitlali. Okay, I will, okay, cool. I will try my best. Cool. Uh, okay, hello, hello. Almost all there. Good morning, Yasmin. Thank you. Um, Yaverbaum. It's all about why. Actually, my dad is really obnoxious. My dad, whose name is Yaverbaum, like obviously, or not obviously, what he would do in restaurants when people would say like, "What's your name? Could you spell it?" He would go, "This is so obnoxious." My dad is obnoxious. He would go, "Y as in Yaverbaum, A as in Averbaum, V as in Verbaum, E as in Urbaum," and go all the way to the end. Like, who's not hating who by the end of that discussion? But okay. Oh, and sorry. So, okay, this is where we are. Oh, aren't all of that? Yes, all of our parents are totally obnoxious and embarrassing all the time. And I'm speaking for both of my sons when I say that too. Yes, parents are our biggest liability in life. We all have to bear that luggage, um, and yeah, being a parent is, yeah. Okay. Although I'll also say one funny thing about, or I don't know if it's funny, the very first year I ever taught, like my very first year of being a teacher, and at that I was a high school physics teacher the first time I taught, and it was 1992. I just turned 21, and I had my first teaching job. It was in New Orleans, Louisiana, which is I loved. And my dad came down to visit me, and he watched me in one of my classes. Actually, we pretended he was a board member. We scared the crap out of all the students. They thought I told the students in advance that I was being watched by a board member to see if I could keep my job or not. And like everybody had to behave and stuff because this guy in the back was going to be watching, and he was like going to be in a 3-piece suit and everything, which he was. But it was actually my dad, but like, and the whole class held its breath the whole time. And that was all an intense thing, which is kind of wild. But then, and so that was the first time he had ever seen me teaching, because it was the first time I was doing it. It wasn't the first day. But then we're like, at night, we're going across the street in New Orleans to a restaurant somewhere, my dad and I, and again, I'm like 21, and a whole car of teenagers like drives down the road, teenagers like juniors and seniors in high school who were in my physics class. And they all shout out, and remember, I'm a teacher, I'm their teacher, even though they're like 5 years younger than I am, but and they shout out of the car, "Hey, Mr. Yaverbaum." And I totally do not look up at all. I assume they're not talking to me. And my dad totally looks up, assuming they're all talking to him. And they were talking to me. And it was the first time in my life, like I was Mr. Yaverbaum in front of my dad, and it was very strange. And one of those kids was Peyton Manning, by the way, if you follow football. And that's not a joke. Peyton Manning was in my very first physics class ever. And literally, if you know who he is, he's an NFL quarterback. And when I don't know why I'm babbling, I'm just warming up here. Sorry, but this is a true story. When Peyton Manning actually signed on, to go to Tennessee and play football for Tennessee, like he was signing on to Tennessee, but all he was a kid in high school, like picking his college. He's just like a kid in college who got accepted and was now going. But nonetheless, the entire school had a full-on assembly and a ceremony where Peyton Manning went up on the stage and signed the like "I'll go to Tennessee" document, like just a freaking kid going to college. But we all watched as he like signed and celebrated the beginning of his career. It's very weird, but he's a cool kid. And he was slick about cheating. Okay, all right. Oh, sorry. Okay, I'm gonna read the chat. Sorry. Well, it was, yeah, but now it's real football. I mean, now it's NFL, but yes, you are right. Yes, am I right? Up top, you are right. And people get totally confused. Luna, I just ate you. Can I say that? No, I'm not even going to say this, but this is the first time in my life I've ever had a student named Luna. And at the same time, an old physics student of mine who's now a physics teacher in Chicago, he has a student named Luna that he wrote me about just because he thinks that is interesting. So that's a great name. I mean, but for putting up, we should. Yes, you should get signing bonuses for signing up with Zoom University. You should, and I hope that my younger son gets a Nintendo scholarship to Nintendo University. The way this Zoom thing is going. Okay, you guys. You're welcome. Okay, you guys are totally on top of the homework. I should get rolling here because I'm very pleased. Like, let's make this clear. I think I've gotten the number line, the first, even though we have not finished going over the first assignment, and I know that, and we're here to start doing that, but I've gotten the first assignment from everybody in the room, I'm pretty sure. And I think everybody in the room got it back, which is good. And I hope everybody notices that even if I wrote like okay next to something, or if I write will discuss, or if I write BCF, which I don't think anybody saw on their first assignment, but you might see on your second. If I write BCF, that means be careful. Stupidly means be careful. If I say anything like okay, or be careful, or we'll discuss, what that means is right. I'm like not agreeing that this is the correct answer. I'm saying it's not the correct answer, but notice you still got a 50 anyway. I think every single one of you. Now, the way to not get a 50, and we're almost on the verge of this is going to start happening to people. The way to not get a 50 is to not address certain questions, like to leave them blank, or just to start them in kind of a weak way and not follow through. I want to emphasize that you can get a 50 out of 50 for totally wrong answers, but what's great about this class so far, and I'm saying this, like some of the answers at the end of the first assignment were wrong, or I think in some cases. Let me go on and say I got the second assignment from just about all of you, which is awesome. And I know we haven't even begun to talk about it, which is great. But all of you, just based on the definitions given in the sheets, or maybe for some of you based on your prior experience in life, like most of you turned in the second sheet already. That is fantastic. I think all of you got it back. I'm hoping, or tell me if you didn't, you should have all gotten back. Now on the second sheet, and we're going to get to this. I mean, I'm just trying to like administratively catch up here on that second sheet. I hope many of you will see a lot of you got the first three questions like totally right. Some of you made maybe a little like left out a units thing or something in one of the three questions or something, but most of you got the first three questions right, fine. Some people did amazing correct work on question 4 and 5. A lot of people got question 4 and 5 wrong on the second sheet. I want to emphasize again, I want to make this clear before we go on. I want you to notice you could get the answer totally wrong, or I hope it's clear, or you could get an answer that I did not say is right, but you still got 50 points as long as you put in work and you got an answer. I want to make that clear because the physics is going to get harder. I mean, it is. And I want it always to be the case that what you're trying to do is get answers and be okay with getting wrong answers. In fact, let me go a step further. So I'm very impressed though. I think like we technically have train of thought, like the next assignment is due next. I don't think it was meant to be due today, I hope. And if it was, I'm extending it. Did I say train of thought was due today or is it due Monday? Is train of thought? Yes. Oh, sorry. Okay, so I haven't even, so you're ahead of me then now. Sorry, it was due today. Okay, so let me back up. So if I made train of thought to you today, because it's the third assignment, anybody who's turned it in is totally on time and I'll notice and stuff. And you're ahead of me now. Like, obviously I have to go over sheets 1 and 2 before we can get to 3. And even though I did post a 4 in your stream now, we're going to pause on that number 4, just if anybody's getting worried. Like right now, you guys are kind of ahead of me, which is great. But then also I'm behind you. So there will be a break at 4 for me to catch up and stuff. I'm not going to ask you to think that far ahead or whatever. Even with 3, since we're not going to get to go over 3 today, if you haven't handed in 3 yet, no penalty, no foul at all. Take your time with it. And actually it's kind of a different kind of assignment. So you want to think about it. So don't worry if that, those of you who did already turn it in, it's totally noticed that you did. So don't, worry about that. And I haven't graded any of them of number 3. Now, number 2 and 1, everybody rocked. I'm glad. Pretty much everybody actually filled out an answer for every question. That's what we're looking for here. Most of you even circled your answers or like highlighted or something. I have to say that's super important. Please do. And this is like a science thing, not even just for class. I mean, yes, for class on homeworks, please circle your final answer, make it super clear and, complete it with units and stuff like that. It's clear. It's important for a lot of reasons as a habit. I mean, first of all, it's like really important for publications and journals and research and stuff that you like always know what the ultimate point is and you can always hammer back to it, that you begin with the conclusion and you end with the conclusion and you're always like, you always have to know what the point is. And in a homework exercise, the answer represents that, like the ultimate point. But and you want to make the grading as easy as possible. Like you want me to see that I see the answer. But here's the other subtle reason that you all really do want to circle your answers. And even on by the second assignment, some people that did circle their answers on the first stopped circling on the second, even if they got all the answers. And why that starts to happen, why people stop circling their answers, is they start getting insecure about their answers, right? People, even super responsible people, super responsible, smart people, which all you are, when things start getting a little hazy, people will start feeling a little bit not so sure about their answers. And then they don't really want to draw attention to them. Like they want all the work to be there. Like I did the right thing. Here you go, yo. But they might even be somewhat confident at their beginning, but they know something fell apart by the real answer. And I keep telling everybody, it's about showing all your work. Don't worry about the right answer and stuff. So this is a fine line I'm walking. It's taken me a long time to realize about this line. I'm on the one hand telling you all, please don't worry if your answer is wrong. You're going to get full credit anyway. But I'm also saying, it is about the answer. We're not playing a game here where we're pretending it's not about knowledge. It's just about the journey and how you get there. Like science in the end is our interpretation. No. Like there are answers, right? Like we do want to get to an answer in order to call a problem done. And all of you have been doing this. Like this is why I'm saying this now. We want to get to an answer and we want to circle the crap out of that answer. We want to sort of be loud and proud and say, this is the answer. Even if in our hearts, we're like, oh my God, I totally think that is the wrong answer. I totally think that is the wrong answer. The reason it really matters to circle your answer is because what you're really actually first and foremost telling the reader by circling your answer that says V equals blah meters per second, what you're saying is, I totally get what the question is. The question is asking me for a speed or velocity. I'm giving you a velocity in meters per second, yo. Like I have answered your question. And this is why, if you can actually get to that, which you are right now, but I'm just like, when things get hard, it gets hard to do this. If you can like stand as a scientist and be like, your question is this, my answer is this. It's so that at that point, then even if your answer is wrong, what you've totally done is proper science because you're not being biased. Like you'll admit it when you find out your answer is wrong. And it's like data. You've collected the data. There it is. There's no lying about it. And you're saying, I get that the question needs a meters per second in order to be done. Like that's how I'm done with this question because I got a number for meters per second. So I promise all of you, like, and then if the number is actually 7, but you put 8, like that is such a minor detail here, especially if it's not on an exam. So when we say, so that's why I say it is about the answer, but it's not about whether the answer is right or wrong. Just like make sure it's the right type of answer. Okay. But I think people are rocking on the homework. We're going to start talking about, I see where people get, people don't, we'll start talking about the physics of it now. I think now, wait. Oh, and with the games homework, the class participation thing, I hope maybe you saw, maybe this helps. I did take the liberty of renumbering them and I shifted all the, okay, so I'm just trying to make it clear and organized. Every day you have the next turn in the game, which is your turn, your opportunity to record where you class participated a little bit if you want. And I'm just technically, I just renumbered them all and saying, considering that we all did this together on the first day of class, like I actually asked you all to turn in that day, you actually all gave me one on that first day. So I'm just hereby formally saying, okay, for like day one was turn one, it was due 20 minutes after class that day. Then the next class, the one for that class was due 20 minutes. Just in other words, like once you sign off for class, take 5 minutes to just jot the thing down before you forget. Turn three was for the third class. Now, again, I don't care if you hand them in late. The dating system is just to keep it organized so you can keep track of what's going on. So I'm just arbitrarily saying for any given class, like today's our fourth class. Today's our fourth class. So turn four is due a half hour after class. And again, also, if you never hand it in, I don't care. But if you, so that's how, and then any of the special ones that are special, like today I threw in another one, which is anytime you use your voice, if you use your voice, not only can you count that as participation for the day and throw it in for the 50-point bucket, but if you actually use your voice, also throw that same memory into that 75-point bucket that says voice. And, that one's like due whenever it's due in May or something. So it doesn't have a number on it. So I just tried to, hopefully that organizes the numbering system, makes the whole thing more clear. So technically turn four would be, and again, you can go back and retro them. All right, I'm going to stop for a second. Is this all clear so far? Like, I know it's boring. Is it? We can start doing some physics now if that stuff is, but stop me if you have any question at all. When I say we're going to do some physics, I mean we're going to start sort of going over sheet. We're going to do this. Correct me if I'm wrong, but I believe that even though I've shouted out some answers to sheet one, and even though I know that most of you got the early answers right, I've not like formally sat down and start going through it yet, have I? Like the Smurfs. I don't even get why I like the Smurfs, but I do like the Smurfs. Wait, is this right? Like, should I, my instinct is right now to say, okay, let's start on homework one and go through it, even if that's what we are, where we are, yes? Or have we already, yeah, yes, okay, thank you. Okay, so here we go. Okay. And you'll have to remind me, but as I recall, we got this professor that's the front of the room. There's obviously a fake situation, but what is this all really about? Remember what this is our first homework, and I know you already did it and all that, but this is our first problem or introduction into this world of one-dimensional kinematics, right? Like the thing to focus on is that we have one dimension that we're living in, one degree of freedom. That is to say, one choice at any time, whether to go forward or backward, or whether you want to call it left or right, or north or south, whatever it is, it's one degree of freedom. And therefore, we have this convenience where if we want to distinguish our two choices, like at any moment, we have a choice in direction. If we want to distinguish one direction from another, we have this convenient tool from numbering systems in mathematics where we can use negative signs, right? Like this is a convenient, like it can work out that we can think of this whole world as like a number line, but that has positives and negatives on it. The negatives indicating one direction, the positives indicating the other. Now, it may or may not be obvious, but but I can't draw. It may or may not be obvious, but that I'm picking left to be negative and I'm picking right to be positive. Everything we're going to do could work just as well if I made the opposite decision. There's no, God did not tell me that right is positive. And well, I'm not aware of any like dictum in the universe that says that right has to be positive, and it doesn't. It traditionally often is, but it doesn't have to be. But the key is just note from the beginning, we're making a decision and notating it. We're choosing, say from here on, I'm going to use positive symbols to denote that way, and I'm going to use negative to denote that way. And that decision is going to apply to anything I do in this world, like whether I talk about displacement or velocity or acceleration ultimately, or force or something. We're hereby designating to the right of zero as positive numbers, to the left of zero as negative. And by the way, where's zero? Wherever the heck we say it is, right? But then we're going to stick with that. Okay, so this professor happened to start, and again, tell me if I'm wrong, but I think, and I can never draw, whatever, but there's this guy, and he's not at -3, he's at -4, right? Stop me if I'm wrong, but I believe, or please confirm someone, if you want class participation points, he does start at +4. Is yes, thank you very much. Okay, awesome. And I still don't get the Smurf thing, but cool. Okay, so there he is. And then the facts that they tell us is that the professor, in effect, and this is, you have to diagram this your own way. There's no, it's hard to diagram this because I want to now designate 3 different stages of time all in one space. So I'm like making up a way. I only have one space, one dimensional space to work with, but there's 3 different time segments that happen. And oh, and I'm sorry, and I believe the last one was wrong. It goes, he ends up at the, oh yeah, this is what does he do again? He goes to the -5, then back to the 4, and then he goes to, where does he end up? Could someone remind me where does he end up? Because I'm not looking at this.
He ends up at the -5 mark.
Oh, he does. So he goes, so is this right? I don't know why I'm suddenly not right. Does he go from +4 to -5, then back to positive? He goes from 4 to -5, and then back to 4, and then
In the first one, he goes from 4 to -2, then
oh,
-2 to 4, then
oh,
from he goes to -5.
thank you. That is awesome. Okay, I appreciate. I was not. That was not a trick to see if you were paying attention. I totally couldn't remember. But it does help to know people were great. Right. So he goes from 4 to -2, and that first segment, if I recall, takes him 3 seconds. Is that, someone correct me if, and then
Yeah, it takes 3 seconds, then 2 seconds, then 3 seconds.
okay, great. All right, thank you. All right. Right. Okay. Sorry. So this is a situation right now. Really, this whole exercise, and again, I hope that the first like 4 or 5 questions are somewhat straightforward. I think it gets a little tricky after the first 5. But what's the purpose of this whole thing? The purpose is to define our terms as physicists. Like, we are here to study things moving in space and time. We're first going to look at the simplest, purest situation we can, which is something moving in one dimension of space. So now we're going to start defining our terms, like defining how we can met whatever measurements we could possibly make in space and time, right? So so we start off by saying, okay, there's a concept called there's a concept called distance, which is just how far in space we get, just what size segment of space we're talking about, what chunk, what interval from here to there, that's called distance. But then displacement, I know you read this in the sheet, and it's clear that most of you understood this. Displacement is the more complicated, like richer concept of distance plus direction, right? As a concept, that's what displacement is. It's what is your distance, and let's take into account whether it was a distance that way or a distance the other way, right? Now, these are just 2 different words. We're just basically saying right from the get-go in physics, we're going to want to acknowledge sometimes that direction matters. And maybe sometimes we'll not need to acknowledge that. So we just have 2 different words for it. But the bottom line is that displacement, since we designate directions with positive and negatives, as I'm sure you saw on the sheet, displacements can be negative, whereas distance never can by definition. And if you take any for any one interval, distance is the absolute value of displacement, if you like. For any one given interval, distance is the absolute value of displacement. But if you have a series of intervals like this, you may have noticed, I'm intentionally saying this in English because I don't want to give you a formula or anything for this yet. I'm just trying to work out the logic. If you have intervals like this, like 3 seconds, I do this thing, then 2 seconds, then 3 seconds. Well, the entire distance for all of that would be the sum of the absolute values of the displacements, right? And in other words, 3, I don't care what, just +3 plus +2 plus +3 would be the total distance, whereas the displacement would be negative. I didn't mean +3. I'm sorry. I meant +6 plus +6 plus +9, right? I'm just going to write down the answers. I mean, I know everyone got this right, but the total distance absolutely. Here, I'm going to go on the next page. Let me show you. This is what it really needs to do homework, I think. Whoa, well, sorry. I don't know what just happened. Sorry. Whoa. Sorry. God, that's like everybody's worst nightmare. What would happen if I don't know what happened? Hold on, sorry. I'm dragging something. I know the answer. The answer to the first one was 21 feet. I think pretty much everybody got it right. I'm hoping that it is. I don't think anybody's sitting here desperately needing me to explain why it's 21 feet. But what I want to do is take the case of 21 feet, since it is an example that I think everybody's comfortable with. I just want to break it down for a second and show you what it would mean to show work here for 21 feet. Like for most people, they would get 21 feet so fast in their mind that if I ask you to show work for that, for most people, that's almost insulting and obnoxious. If I say show your work, most people would be like, my work? It's like 21. It's like 9 plus 9 plus 6. Like, what work do you want me to show? And in fact, you might even think, if I say show your work, that you're almost thinking, are you like actually asking, like you think I'm cheating? You actually ask me to defend? Like, do I have to justify why it's 21? Here's what I'm saying. When we say show all work, we're not showing all work to like as a way of showing that we didn't plagiarize. We're showing all work to break down how we got the answer into steps. And the thing is, on really easy questions, people can run through the steps so fast in their mind that they think that the answer is just obvious. Like they think there's no steps. If you're smart and you're fast and you got other things to do in your life, you could be like, the answer is 21 feet. How do I know that? I just know, like I just did it. Like I see it. There's no steps to do. But actually, that's not giving yourself enough credit. You did at least 2 steps really fast if you get to 21 feet, which is that first in your mind, you asked yourself what distance actually means, like because that's what this whole sheet is about, right? Like for example, if you got the first question right and you get the second question right, that means somewhere in your mind has absorbed that distance means one thing, regardless of what the numbers are that we're talking about, and displacement means another thing, right? So what your mind does, I mean, I believe on the first question is it goes, what does distance mean? Oh, it's that thing where I just add up the numbers. And then it goes, okay, so what are the numbers here in this problem? Oh, it's like 9 plus 9 plus 6. So in other words, notice here, I use a triple equal sign. This is why I'm introducing you to a piece of notation you may not know. First, I say distance triple equal sign interval of space. And then that might not be the best definition, but like that's my definition for the moment. I'm saying what distance is defined to be is the interval of space. Then I'm saying distance double equal sign in this case is 6 feet plus 6 feet plus 9 feet. And this will look more and more like equations in a moment. Like right now, these are English words. But what I'm saying is there's 2 different kinds of equal signs in this world. And physics is a lot easier if we keep the 2 kinds straight right from the get-go. From here on in, I'm saying we're going to, sorry. Good question here. Sorry, pause for a second. A good question in the chat that happens to be a private question. So I'm not gonna say who is it, but it is a good question. There's no reason it needs to be private, but what does it mean when the displacement is negative? Very fair question, by the way, because like that is the whole point of the sheet. And there's different ways to say this, but negative means to the left. Positive means to the right, like in this sheet, literally and fully. In general, negative and positive denote one direction versus the other. In this case, it's like left and right. We could turn the whole sheet and make it up and down, or it could mean north and south. So in every new fresh physics problem, we start every physics problem by actually making a choice, even in the simplest space, like even if we only have one axis, like here, we start before we even solve problems, we make a decision. Okay, that direction I'm going to call positive from now on. Anything that goes that way, I'm going to call positive, and anything that goes that way, I'm going to call negative. So 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 this is a good question. So the first question on the homework is asking us for distance. Distance as a concept does not care about direction. So distance is always, the answer to any distance question is always a positive number. The answer to the very first question on the homework sheet is 21 feet. But what I'm actually trying to say right now, so I hope I answered that question in the chat. I'm not sure. Someone can like follow up if they want. But what I'm trying to say right here is I'm trying to, on purpose, I don't want to bore anybody, but I'm on purpose trying to talk about something that where I think everybody does know the answer. And I'm trying to show you what secretly like work went into you getting the answer, even if you thought it was really easy work, because this is the model that we're going to want to follow when we don't know an answer or when we think the answer might be wrong. That is, I'm saying you can't get 21 feet really, no matter how fast you do it. What you really have to do in your mind first is ask what's the meaning of distance. And then once you realize some definition or equation or formula for that, then you're plugging in the particular numbers of this question. So you're actually taking a general definition that's always true and right and saying it in your mind first. And then you're applying it to what's relevant here in the problem second. The reason it's, and you can literally show that. And so even at a minimum, this actually technically is 2 steps. And it's almost 3, but it's at least it's actually 2. And again, I'm not saying anybody did anything wrong here on their homework, but I just want to start breaking things down and introducing you. There's a difference between a definition and an outcome, or there's a difference between a definitional equality and an outcome equality. One big difference is that definitional equalities are literally never wrong. Like they're strictly, literally never wrong. They're infallible. Like if you say like a square is a 4-sided object, right? Or if you say a square is a 4-sided object, first of all, that's not just like a rough, like a weather prediction. You're literally saying that for all time. If that's true at all, it's always true. Better example of what I'm saying is like, if I walk in the room right now and say, hey guys, how are you? I had a great trip to Philadelphia this weekend. As a matter of fact, down in Philadelphia, I saw a couple of 3-sided squares. It's unbelievable what they got going in Philadelphia. 3-sided squares, right? If I said that enough times, like at some point, one would be like, no, you did not see a 3-sided square, dude, right? And I mean, hopefully one of you would say that. And then if I'm like, oh, really? I didn't? Like, have you ever been to Philadelphia? You've been to the south side of town? There's no, but you'd be like, yes, like I don't have to go to Philadelphia to know that there's no 3-sided squares, because by definition, a square is a 4-sided thing, right? Definitions, like if they're right at all, they're literally always right. So that means whenever you're solving problems, you always start with a definition or something like that, because even if, God forbid, you're misunderstanding something later on or doing your numbers wrong or don't know where to go from there, if you write down a definition, it's definitely right. It's definitely right. Even if it accidentally turned out to be irrelevant, it's definitely right if it's a definition. So that's points right there. If it's an exam or homework, you're getting points for writing down something right. The converse of all this is when we start getting to problems where you might feel, I don't know what to do. I don't even know what this question means. I don't even know how to start this to get points. The way to start always is with a definition. When in doubt, start with a definition of what? Of the key terms in the problem. Particularly if you think you don't even know what the problem is asking, what you do is ask yourself which words are weird and define them. Like for real, it's all about definitions first. So we're going to spend a lot of time on these definitions. So in fact, well, yeah, so I'll bang through a little bit more but distance is just defined to be interval of space. There's not even an equation for it or anything. Displacement, however, okay. Now, this is still English. I want to start converting this English into symbols and things that look more mathematical. All math is just a symbolic way of expressing English. I mean, so we're going to start translating this into symbols. We're going to start translating into symbols. I'll get a couple of answers though first, just to make sure we're all on the same page. Like by this definition in English, it seems to me that for question 2, if we're asked for the total displacement, for question 2 was, what is the total displacement for the whole journey, the whole sum of the 3 intervals put together, right? So how would I do this if I'm doing homework, right? I might say something like this. Actually, I'm going to do it on the next page. Yeah, I'm going to do it on the next page. And you can tell me to go back if you want. But if I'm doing this in English, and again, we're about to depart from English, but okay, these are the answers to the first 2. Again, oh yeah, oh no, good. Okay, I think everybody knew that. I want to make this start look, I want to not write so much. I don't want you to have to write so much. I want to be able to express this a little more simply and move a little faster. I'm sure everybody would like me to. So we want to start converting these like into letters and symbols and things that look more like math. Okay, so what I want to do now is before we even get into the average speed, so the next 2 answers, we now define a new term, average speed, right? And we say that, and we define average velocity. I guess I should, all right, we'll just, yeah, okay, we'll do this just so we can catch up with ourselves. And also because this now relates to the second sheet. So this is all, so we basically start by saying we're looking at space and time here. In physics, everything is about stuff in space and time. So space, we've decided to look at, like we're scientists, so we're measuring. So we need a way to measure space. We measure space in meters or feet sometimes. And we just realized right away, we can measure sizes of chunks of space, or we can be very precise and clever. And sometimes when it matters, we can not just say this chunk is so big and say this distance is this number, but we can sometimes say, what about going this way versus going that way for a certain chunk of space, and we call that displacement, right? So that just covers our 2. So far, we're like, there's 2 kinds of things we should track in space. There's size and there's direction. We got it. Now we say, well, how does that relate to time? Like things move in space, but they also move in time. And in fact, time itself always seems to be moving. So what's the simplest way to put these 2 concepts together? The simplest way is a ratio. And I'll tell you why. But so we define this thing called average speed. And again, we're still in English here, for good or for bad. We're almost out of English. We define average speed to be some total distance that's covered over some total time elapsed. And we're going to be consistent right from the get-go. Like when so this is a definition now. This is a definition. Average speed is just a word that stands for the word distance divided by, or whatever number you get for that, divided by the number that you get for the word time. Okay, so no one discovered this. We're just saying that we're going to substitute one word for a bunch of longer words. But what distance and what time? Well, if this concept makes any sense, if we're measuring, if we kind of start talking about people's average speed, what we mean is the average speed of something from one point in space at a corresponding point in time until some other point in space at the corresponding point in time. Like there's some way in which we have to be consistent here, right? But if we, as long as we keep ourselves consistent, then we can talk about how fast someone's going in terms of how much ground they cover per each unit time. By setting it up this way, notice it just becomes the case that the faster you are, the faster you move, the more ground you cover per time, the higher your speed number is. Notice we could have decided to do this the other way. We measure how fast things are. We could just as easily and consistently measure how slow things are by saying time over distance. There'd be nothing wrong with that. It would all work. but we want to be consistent. We happen to choose to look at the world this way, that the more distance that you cover per unit time, we call that your speed. But then we also recognize, oh, but wait, what if we're tracking direction? If we're tracking direction, then we invent this concept called velocity. Now, you've heard of this. This is where things start to get a little bit subtle. In English, and it really does get subtle on the second sheet, some of you may have noticed, like I am now saying that average velocity is defined to be total displacement over total time. We've said that displacement can be negative. That means average velocity totally can and often should be negative. We're saying there's a difference. We're saying you can go 30 miles an hour in your car, that could be a velocity, or you could go negative 30 miles an hour in your car, and that would be a velocity. And that would simply mean that you're going 30 miles an hour like to the south rather than to the north, or to the west rather than to the east. I mean, the minute you turn around, you're going to flip your velocity from positive to negative. It doesn't mean you're going back in time or some weird thing. It also does not mean you're slowing down. It just means you're going in the other direction. So velocities can be negative and velocities can be zero, but this is going to start getting very clunky. Oh, and by the way, if you got question 4 and 5 on the average speed sheet, if you're really strict about applying this definition, you can get them right. But if you unconsciously apply some other definition that we're not saying, for example, a lot of people in question 4 and 5 on the second sheet, on question 4, a lot of people wrote 50 because the average of 40 and 60 is 50. The average of 40 and 60 is 50. But, and this is a subtle point, but notice no one here is saying that average speed is defined to be the average of speeds. Like if you averaged a couple of speeds on question 4 in the second homework, I totally get why you would do that. You're not a dummy and you're totally being responsible. It's like a thoughtful, but it's actually not anything that anybody was ever given permission to do. I mean, like not permission, but like, I just wanted, what I'm really trying to say here is average speed might sometimes somehow end up double equal signing average of speeds. Like sometimes average speed could be equal to the average of some speeds, maybe sometimes, but it's not defined that way. The average speed for some intervals, just how far you got in how much time, not necessarily the average of any speeds. So this definition will sometimes not seem useful, but it will always be right, particularly in the second sheet, just like as a warning, whatever. But now that we're getting into all this like dividing by and stuff, it's sort of time before it's time. Oh, is that where we go? Okay. It's time. And I will take a break and see where you're at in a moment, but I want to just move along a little bit. I want to start turning some of this English into math, I keep saying. So I'm going to start taking some of our definitions and breaking them down a little bit even further. So I guess I'll say, did I get an answer? Yeah, I got an answer to the last one. I will say, I guess for question, just to be clear, for question 3 then, or problem 3 or whatever it's called on the homework, when it's asking for average speed for the whole journey, again, I would say like average speed is supposed to be distance over time. So in this case, average speed for the whole thing, double equal sign, 21 feet over 8 seconds. So, yeah. And this is starting to get cumbersome to write, right? Like even these things that may be obvious to some of you, I'm already asking like to write a lot stuff down. It's one of the reasons we want to shift away from all this English, but this would be the answer, right? For question 3, the answer is like 21 feet over 8 seconds. You can write that as 21 over 8 feet per second. You can reduce the fraction. I mean, you can say it's 2.375 or 2.4 or whatever feet per second, but you don't have to. But also notice, like I'm a scientist, I tend to use the metric system. Like we do prefer meters. Ultimately, they're easier to work with than feet, but feet are still legal and legitimate. If the facts of the problem are being presented in feet, then your answer is in feet. I mean, unless told otherwise. You don't have to do unit conversions unless you have to. So the answer is like 21 over 8 feet per second, or you could write it some other way, but this is totally acceptable. Question 4, same, just to get this straight. We now ask for the average velocity. Okay, so average velocity, same thing. Average velocity is defined to be displacement over time. So now it's a different definition. We're going to plug in different numbers. But what are the numbers in this case? they are -9 feet, because we got that from the second problem, over 8 seconds. So that is like, you could just write it like that, or you could say like -1.125 feet per second. But the answer is a negative number. On average, this instructor goes, on average, it goes a velocity of -1.125 feet per second. That means on average, every second, the instructor moved 1.125 feet to the left rather than to the right. That's all the negative sign means. But it certainly can be confusing or weird at first. But you never have a negative sign in any speed answer, but you always could have a negative sign in any velocity speed answer. Put one last final way, like in a regular, well, no, I think you get it. I think you get it. I'm just looking at the chat. All right, let me just start converting this. Well, is everything, I know this is boring, but is everything clear so far? Is any questions at all? I know we want to get, and every time I say it's boring, if you're secretly confused and I say it's boring or clear, that you're still allowed to, that's my insecurity. Like, you're allowed to have a question or be confused. But if not, all right, I want to depart a little bit. Like, we'll keep getting the answers and we're going to get to the point where we're at harder answers. But I want to give you some notes for a second, some definitions that are working underneath the scenes and that will turn this into math. So here's, like, I'm talking a lot about space and time. What the heck do I actually mean? What are space and time? Like, we all know, in a way, we know what we mean by space and time in a way, but we also know that none of us can really get at exactly what either of them is, or in what way. I mean, they sort of seem similar, but also similarly confusing. Now, on the one hand, let me say, in physics, we tend to assume that there's space and time and then try to analyze all these motions within it. But the deeper and deeper you go in physics, just to be clear, it ends up being that we are investigating what the heck we mean by space and time. Like, the simplest things in life are not the easiest things to analyze. They're the hardest things, right? We'll get more into that. But what's hard about physics is not that it's complex. It's not. Physics does not have a lot of details. It does not have a lot of equations or formulas. It is nothing like the amount of knowledge or information or material that you're used to having to know in bio or chem. It just doesn't. There's not a lot of information in physics, but that's what makes it hard, that there's not a lot to break down. Like, we're interested in super simple things like space and time. And, if you want to break down a unicorn, you're like, oh, it's a horse with a horn on it. I can break that down. A unicorn is complex, but you can break it down. It's a horse with a horn. But then someone asks you, what's a horn? And that's a little harder. That's weird. Like, what is a horn? So simple things can actually be not easy, right? And that's what tends to go on in physics. So let me give you our working definitions of such simple things as space and time. When I say space, for our purposes for the moment, when I say space, I'm going to use the definition that actually comes from Einstein. Believe me, this is literally a definition that it took till 1905 to become like sort of the working definition of space to a physicist. And you're going to think it's a joke in a way when you hear it, because it almost does seem silly. The definition of space is okay. And before we even discuss it or anything, and the word that and the word that which, I don't know if it's that or which, but first I'm going to say, what is space? When we say space from here on in physics, what we mean, and bear with me, we mean the interval. So space is an interval. That's like a segment or a chunk or a separation or something like that. Space, when we say space in physics, we mean an interval between 2 points. So, okay, we're imagining 2 points, like 2 dots, like Euclidean points. Imagine 2 points. Now imagine the interval between those 2 points. And we're going to say that if you're picturing an interval that you could measure with a ruler, then we're talking about space. Now, weird definition in a way, but partly what it's getting at right away is this is not a philosophical definition of space. It's not a religious definition of space or whatever. It's a science, and it's not even a mathematical definition of space. It's a scientific definition of space. And what makes science is measurement, right? Like, ultimately, the thing that makes science different from even math is that everything begins in science with trying to get a number out of nature, to measure something in nature. So we define our terms by how we measure them. So space is an interval between 2 points, which is measured with a ruler. I'm going to go on for a second, as opposed to, as opposed to time, which is an interval between, and this is Einstein, right? And there's a reason Einstein is Einstein. It's not because he like spins all these complex equation webs. It's because he knows how to break things down to their simple parts, which is hard. But time is the interval between 2 points that is measured, or that can be measured, as you can imagine, with a clock, or that is measured, whatever, measured with a clock. Because if we can't measure it, we're not talking about it in science, like, right? I love love, and I love to think about hate and injustice. They're real, they exist, but I don't think about them scientifically because I can't like measure. I don't really know how to measure like love or justice or whatever. If we're going to talk about it in science, it's because we can measure it. So now space is one kind of measurement. It's the kind you make with a ruler. Time is the kind you make with a clock. But now notice also what's common between the two of them. They are each an interval that is measured between 2 points. 2 points. What do I mean by these points? So I'm going to go on for a second. But notice, like, in other words, in English, we actually use the word time in 2 different ways, at least 2 different ways. And we use it without being conscious of it. And we use the same word in 2 different ways, which can get confusing. In other words, sometimes we say in English, oh my God, how much time does this class last? This class lasts for so much time. It lasts like 75 minutes. That's a lot of time to spend in this class. That's one way of using the word. The other way to use the word is this class over yet? What time is it? Is it time for class to end? What time is it? Is it the time that the class, that's the other kind, right? Like 3:05 p.m. or whatever is the time versus time that the class lasts. I'm saying now in physics, we want to make that distinction straight right up front. There are points. We don't call them time or space. They're points, and I'm going to give you a definition of them in a second. But the stuff in between, in other words, when we say time in physics, we mean the kind that is like hour and a half. When we say what's the time, we mean what's the interval between 2 certain moments that you have in mind. And so what I'm saying is, so what kind of points, in fact, I'm now going to go back a page. What these points are actually called in physics, they're called events. I'm doing this on both. Space is the interval between 2 events that can be measured with a ruler. This is physics definitions. Time is the interval between 2 events that can be measured with a clock. An event is a point in space and time. That is to say, now we're going to start getting into, is this that, yeah, in the world that seems to have 3 dimensions of space and 1 dimension of time in it, right? In that world, an event would be a like an ordered pair, except an ordered group of 4 rather than a group of 2. An event would be something that is uniquely specified by 4 coordinates, 3 space coordinates and 1 time coordinate. What I'm trying to say here is that in English, and again, we're not trying to depart from English, by the way, and we're not trying to confuse things. We're trying to use all the meanings that we already have in our mind from English, but we're trying to be more precise in English, right? So, so in other words, in English, we use the word event kind of different loose ways. Sometimes we could talk about like the Jay-Z concert that was a big event of the summer or something, or once upon a time when like there was a world and there wasn't a virus. You could say like, oh, the Jay-Z concert is an event. Like some people talked about it, fine, in English. But in physics, the Jay-Z concert is not an event. The Jay-Z concert is a whole series of things that happen between. What's an event in physics is this, a clap or a light flash. An event is a point in space and time. So the moment that Jay-Z or whoever, like the moment someone snaps their fingers and calls at the beginning of the concert. That's the beginning of the concert. That's event one. And the end of the concert is event final or whatever. But an event is a point in space and time. So like if you think of the whole world as a big grid, as like a big 4-dimensional grid, if you can sort of picture that, an event would be any point in that grid. And then space and time are the different kinds of intervals or like segments that in our mind we can draw between these points. And there's positive and negative signs going on. So to be even more specific, I'm saying then a position being a little bit confusing right now, by the way, because I'm just trying to give you the big broad definitions of space and time and stuff that we use in physics. So right now I'm actually defining this for the whole world. Like I'm assuming a complex 3-dimensional, even if we don't know how to do all the math yet. I'm saying in the world of 3 spatial dimensions, an event would have 4 coordinates, X, Y, Z, T. The position of something would be the spatial coordinates of that event. A position is a point in space. It's the spatial coordinates of event, the first, in other words, X, Y, Z. And that's as opposed to, and tell me if you want me to go back, I'm going to flip the page here. Tell me if that's position would be point in space, and instant is point in time, i.e. the temporal coordinate, so to speak, the time coordinate. Of an event. That's what an instant would be. So again, just to like try to map this to the English. So strictly speaking, if I say, is class over? What time is it? Is it 12:05 p.m.? And you say, yes, it is 12:05 p.m. Class should end now. Yaverbaum. That now that you're saying, or class ends now, that's an event, but specifically that's an instant you're talking about. That point now, what time is it? You're asking for an instant. If you ask how long is class, then you're asking for a time interval. And this in physics. And it's very important to distinguish between the two, because fast note, just to tell you why all this matters. It turns out that what's much easier to calculate always is intervals. They're always much easier to calculate, but they're always approximate and not strictly right. But measurements for points are always strictly right, but almost impossible to calculate or to measure. So it's very important, just like triple equal signs and double equal signs are important to keep straight. It's important to keep straight events versus intervals in space and in physics. We're almost there. So that's instant. So then now we can turn this into math. So from now on, we're going to use that may sound weird, but it's true. So we're going to use X from now on to be the measurement of position, right? So from now on, that number line that we're picturing in this whole homework problem, that number line, like from here on in, we're going to call that like an X axis, so to speak. And X denotes where you are on that axis, what your position is. And it could be a positive number or a negative number. It all assumes a certain zero that you chose. And then we're going to picture always some time axis. We can't always draw it in the same drawing, but there's a time axis, and anything that's to the right of zero in that time axis is positive, and anything to the left of zero is negative. Now, what the heck does that mean? Well, it has to do with what's zero on your time axis. The fast answer is 0 on your time axis is whenever you start your stopwatch, whenever the experiment began, which really means whenever you start paying attention to the experiment. Like time equals 0, and just like distance equals 0, you choose. Like center of the room, you call it 0, whatever you pick. Same thing with time. What you call time equals 0 is when you started measuring time for whatever phenomenon you're looking at. So if it turns out that anything ever happened before that, that would be called negative time. It doesn't come up as much, but it just means before you started paying attention. So we use X to mean position. We use T to mean time. Almost there. So I know I'm just like vomiting this out. But then from now on, we're going to say, from now on, we're going to say X sub 0 from now. Okay, here's our first piece of actual real physics. I mean, you may have seen this in high school. It may not be new, but like I'm introducing it now for this class. From now on, if you see X with a 0 subscript, first of all, and I know some of you know this, but first of all, the way you read this, this is now going to become sort of important fact. Okay. Again, you totally may have seen this in high school. I want to start being explicit now. And if you did good, but if you didn't, don't worry about it. And let's even let's like relearn it for the first time here, just to, from now on, if I put a 0 subscript next to an X, or as it turns out, if I put it next to anything, the way we read it, whoa, hello, just lost the universe. Okay. The way we read, oh, I'm sorry, there's something in the chat. Let me just make sure I didn't like. Oh, cool. Thank you, Sonia. She probably said that like 40 minutes. Yeah, 15 minutes ago. It was the last time I looked at the chat. I'm sorry, but thank you, Sonia. So I guess 15 minutes ago, I was clear. Now, God knows where. If you put a 0 subscript next to an X, first of all, the way, or if you see that in a book or in the homework or something, the way to read it out loud is to call it X naught, like, which is often spelled that way. Sometimes it's spelled with a N-O-U-G, but not like in British or like in proper English or in like the Queen's English or something. Not means nothing, like zilch. So when we call X naught, what that really means, by definition, if I put a 0 next to the X, it doesn't mean that X equals 0. Like X naught may or may not equal 0 in a situation, but what it refers to by definition is it means the X value at time equals 0. In other words, when you started the experiment, when you started paying attention. And so what we're really meaning by, so what this is often, so since X measures position, X naught means the initial position of some object that we're researching or observing, measuring, doing an experiment with. In this case, the teacher at the front of the classroom. X naught from now on means wherever that teacher, that object first was, whatever position they were at time equals 0. Notice that's one subtlety of this problem. Notice the whole problem started off with the professor at some spot that wasn't 0. Like, that's possible. Right? For some reason, we call the middle of the room 0, but he didn't start at the middle of the room. Wherever you start is what X naught is. So notice X naught does not necessarily equal 0. It might or might not. But whatever it is, it's called the initial position. Note, please, furthermore, that this is a general piece of notation now. When I write this squiggle here under X, I mean like any symbol you can imagine. From here on in, any variable that might come up or anything we might be measuring, such as V for velocity, if we see a V and it has a subscript 0, then that would be V naught initial velocity, and it would mean whatever the value of V is at time equals 0. And it really might not be 0. People often think it is, but it might not be. So from now on, sub-0 naught means initial value. Fair so far? Okay, clear. Okay, I'm going to pretend it was clear 15 minutes ago. So I'm going to go like just even one step further then, or a couple more steps further. Then from here, this means we can start, thank goodness, we can start having slightly better definitions of things. Like I can therefore say from now on, displacement, like we first had a concept of distance. Distance is interval in space. Then we decide we want to be sometimes more precise in physics and really think about displacement, like interval of space, notated with direction. Displacement becomes the more useful concept in physics. So I don't want to have to write it every time. So what I realize is that actually from here on in, for displacement, I can write it as x minus x sub 0, any position. And that means, in effect, final position minus initial position, right? And it looks like it's going backwards in a way, but it's not. Like, it's like, you know, if I'm 5 feet tall now, but last year I was 4 feet tall, then I grew a foot, because 5 minus 4 is 1. I don't do 4 minus 5, right? I grew a foot in time because my final height minus my initial height is 5 minus 4, positive 1. Displacement from now on, I could just write x minus x naught like that. There, oh, right? But by the same token, then, oh, yeah, I could put this over time and I have average velocity, right? So from here on in, I'm going to say, okay, this is just about our first actual real physics equation. And notice, and this is our like first physics equation, but notice it's almost disappointing, because hopefully if you get what I'm saying, what I'm calling our first equation, hopefully you're seeing it's not even an equation, it's just a freaking definition. It's just a definition of English that I'm now just translating into math symbols. But in other words, we're going to start using this equation. It's really important. I'm going to simplify it in one step, but we're going to start using this equation more than you might believe. And I want to stress right here, the reason we believe this equation is not because of some black magic that we're pulling over your eyes. Like, it's not just because scientists say so. But similarly, the reason we're going to believe this equation and use it is also not because we ever discovered it in a lab. Like, this equation will never be proven wrong because it was never proven right in a lab or anything. It's just a definition. But it's like, which makes it sound almost obvious, which is why people wouldn't think to use it. But what it is obviously true and therefore really powerful. So before I circle it and call it a definition, a couple of things. So I'm writing it down. We're about to like box it and call it our equation, but just note the notation. I've just introduced a new thing. Oh yeah, I guess I wrote this, but I didn't say. From now on, if I put a bar over any symbol, that means the average value of that symbol, okay? Now I can't put a bar over X because X is a position, like there's no average position, but I could talk about average velocity being some displacement over some time. And that's just what it is. Average velocity is like the simplest interaction we can imagine between space and time. But remember, we said any symbol like sub-zero, any symbol naught, by definition means the value of that symbol, the value of that variable at time equals 0. Like, we're always treating time as sort of special in physics. Like, I mean, we're always remembering that time is there. So for any symbol such as X or V or A, if you put a 0 next to it, it means the value of that symbol at time equals 0, specifically time equals 0. So therefore, by that, if we do T sub 0, right, that always has to be 0, because T sub 0 means by definition the value of T. Like, it means, sorry, I skipped a step. It means the value of T at T equals 0. So duh, that's 0, right? Therefore, so in other words, X sub 0 is not always equal to 0. It's like a number that we have to, and by the way, I do know it's close to time, so I will, but X sub 0 is something we have to track. Your initial position may not be 0. In the case of this whole problem, your initial position was positive 4. Same thing with V. V naught, people often want to make it 0, but it often is not 0. However, it's safe to believe by definition that T sub naught is always 0. right? That's what I'm saying here. Therefore, I just want you to see, especially since we're wrapping up for today, and we'll go faster and faster. I mean, that is for people like who are like having, you know, that this is like really dull. If it is, I want you to see that our first equation is just a definition of kind of the simplest way to think of space and time at once. It just is, it's like perfectly symmetric. What we're doing to the top is what we're doing to the bottom. We're treating space and time, we're treating them the same way. But because t sub 0 always by definition is 0 always, right? It means I kind of never do have to write that term. The other terms I have to keep track of because they might be there. That one I never have to worry about. So from now on, I'm really actually saying our first equation, we're going to stop in a second. I know there's more answers to get in the sheet. I totally get that. But our first equation for all time is this. It hopefully it's, see, I hope you think it's clear. You might think it's so clear that you can't even imagine why I'm making a point of it. But one of the reasons I'm making a point of it is this is the reason that the answer to question 4 on homework sheet number 2 is 48, not 50. Because if you, and a lot of people actually did rock that, and that's great. And by the way, if some of you rocked that because you went on the web or something, or you even found like old assignments of this from old students and they took, that's totally fine. I just want to say, like, I think it's even more impressive if you thought of that on your own, but no one's trying to fool anybody here. However, any of you who understood by, as long as what you wrote, you understood by the time you wrote it. And I'm not trying to skip around, but just to keep people alive here. Question 4 on homework sheet 2. If you, people want to say 40 plus 60 divided by 2 is 50, but average velocity is not the average of the velocities. It's the total amount of displacement per the total amount of time. And I will go over that question, believe me, I will. But one first thing I could just say to anybody who's, and you can still redo it too, if you got it wrong or you want to think about it now. I'm telling you, if you think about it, the answer is actually 48 to question 4. One way to see that is to realize velocity is displacement over time. Average velocity is displacement over time, or average speed is distance over time. I never gave you the distance of that hill. That's what makes it hard. That's why most people will skip that step and think I can't do it that way. I'll just average some speeds. I didn't give you the distance for that hill. I'm about to shut up. I know what time it is. I'm sorry. I'll look in the chat and I'll shut up. But you don't know the distance of the hill in that hill figure problem. And that's why people's brains shut down and just like make up some other formula to do it. And they're like, oh, and it's reasonable, but they just average 40 and 60, even though we never said you could do that, because it seems okay. Because even if you remember, I should just be able to put the distance over the time. You're not given a distance in that problem. But here's the deal with that problem. As long as you believe there actually is an answer, then the fact that you aren't given the distance for the hill must mean that the answer does not depend on the distance of the hill. If it's possible to get an answer without being given, like if it wasn't a mistake in the problem, and there wasn't, then there must be a way to get the answer without the size of the hill, which means that whatever the size of the hill is somehow still must produce the same answer, which is already weird when you think about it. But if you believe that, which you might want to even just try to believe for a moment, since you're not given the distance of the hill, that means that actually you could just make up a distance for the hill, any number that's easy to work with, and whatever answer you get should be right. That's weirdly lazy way out of it. But in fact, if you just make up any distance for the hill and try it, you'll get an answer. And then you might still not believe what I'm saying is fair or scientific, but then just try a different, make up a different one. And you'll see that you get the same answer again. Go one step further and just call the distance X and just solve it with X in there, and you'll see the X's cancel out, and you will see how, and you'll see that the answer is 48. Again, I'm skipping around, but it's really important to take. So this is our first equation. We're going to stop it there. But our first equation is average velocity equals displacement per time. Why? Because we just defined it to be that way. Let me just, I know it's 12:05. So totally anybody. So I'm going to say bye, meaning bye, thank you. And you could do the same, but I'll hang on for 1 second if anybody has a quick question or something before the next class. But I'm good if you're good, if you could say bye or whatever.
Bye, Professor.
Bye. Thank you very much. Bye. Awesome. Bye. Bye, Catherine. Bye, Daniel. Bye, Jennifer. Bye, Michelle. Bye, Dorina. Bye, Asia. Bye, Luna. Homework guys. Bye. Bye, Raymond. Bye, Yasmin. Bye. Thank you. Bye, Dorina. Bye, Catherine. Bye, Noelia. Bye. Raymond. Awesome. Thank you. Awesome.